Welcome to the medical imaging and big data module of this data science lab course. And so the first thing is I will spend some minutes, maybe more than just some, on introducing the wider context of this course and what we will do and how we will do it, and we will also have some discussion about it. So the first thing is why? What's the importance of medical imaging in artificial intelligence and in big data and so on? That's the number of the medical devices that have been approved by the American Food and Drug Administration by year. Now, these are medical devices. As you can imagine, they have an extremely strict regulation behind that. So it's not like an app on your smartphone that you can code in an afternoon and release and whatever. This has extremely strict regulatory approval, including lots of tests, because you need to guarantee lots of robustness. And you can see that starting from 2018, there have been lots of medical devices that include AI in some ways inside them. Many of them will do really trivial tasks or really not important ones, but have been nowadays even devices that do really automated diagnosis or things like that. And you see, we have more than 1,000 medical devices. So this is, we are not talking about something that might happen in the future. We are talking about reality. Something that is becoming almost standardized, even if it's a very fast-moving topic. The second question is, why medical imaging? This is, if we take from this website by the American FDA, where they publish a list of devices, including AI within them, to any possible extent. Sadly, it has not been updated since May 2025. But if you take it, you see in which field of medicine these medical devices that use AI are working. And out of the 1,000 and something are in radiology. They deal with images. The second most popular field is cardiovascular, where you still deal with some images, and ECG, which are signals. And then you go to all the other fields. But still, some of these include quite a lot of image processing, like ophthalmic. All of these scans of the retina include images. Hematology, there are some kind of image-based blood analysis. And some pathology is looking at slides of biopsies with microscopes. So you can see that the field where AI is mature enough to really be used in the clinical field is really radiology or anything that deals with image processing. Nowadays, there's all of these text-based AI, but this is really not entering the clinical field now. It might be starting right in these years, but it still has a long way for what concerns the regulatory process. Again, why images? I hope you have seen something like this in other courses. There was this very famous challenge called the ImageNet, which was a challenge to recognize objects present in image databases. In 2011, it was the first time that anyone applied a convolutional neural network instead of an handcrafted method, and they got the very best performance ever obtained, even if it was the first attempt at doing that. And in 6 years from then, most of the teams participating in the challenges were having accuracies higher than 95%. So thanks to convolutional neural networks, which work extremely well with images. Nowadays, with transformers, we have some things that might work even better, but with CNN, really, we could achieve performances that were higher, in some cases higher than the accuracy of the ground truth that we have. Already 2016 is 10 years ago. Now, this is the wider context, and this is what this course will talk about. We'll start today with some minor technical details. Let's just do some alignment to make sure we are all on the same page about what's a digital image, how we see it, and how we display it, how we store it, and things like that. Then we will talk about image formation, mainly for these 1.5, 2 modalities, and very brief details about MRI. So when we want to analyze medical images, we need to know what's inside it. We will review some basic pre-processing concepts. Then the things that I've started introducing in the course in the last year is this degree is called data science. So it's technically maybe denoising images and processing images is really at the edge instead of extracting information, but I think it's extremely important, so we'll dedicate one lecture to denoising, which is, by the way, is the basic for lots of theory of image generation also. And then we will talk about how automatic the image analysis is performed. Here are some material. We have an open book which is free to read about medical imaging. Okay, so these are extremely long books. This is a short course instead, but if you need some specific information, you can, if you want to get some information more in depth, you can find it there. You will have a repository, which I will put the link on the e-learning, a Google Drive repository with my slides and some other freeware slides from other centers. And I will also put there all the data for the laboratory. Now, talking about the laboratory, that's the course outline, and this is, by the way, it's mandated by the syllabus. So this course is actually pretty short. We have just 7 hours of theory and 18 hours of lab experiences. By the way, this is the schedule, even if we were discussing about moving the Thursday lecture. And if we work like that, we will finish by, sadly, April 9, because there's the last Thursday before Easter is already holiday. So we will have just one lecture 10 days after the break, after the previous one. Maybe we can schedule it different to finish everything before Easter if we want, depending on what you want. To me, it's no problem neither doing this on this date nor doing before. Now, there's something that I wanted to discuss with you. This course, as I told you, is mostly laboratory experiences. More than 2/3 of the hours are lab experiences. And until now, what I did was giving out some Jupyter notebooks together with some data. And the Jupyter notebooks were empty. They just had the markdown notes of step-by-step what you were required to do. And the lectures were scheduled because this is not a traditional lab. Here in data science, we just stay in the classroom with 3 hours and 2 hours slot. I was starting by introducing the topic, especially after finishing the theory, with half an hour, and then leave the people to program. And technically, it was supposed for me to go around, discuss with you, with the groups, and let you program and discuss the results, seeing what was wrong, what could be done differently. But this was a bit suboptimal. There was low participation in class. Many people did not attend. We know that you have the stage. This is common to all the data science lab. We know you have the stage. Many of you are workers and so on. So, and by the way, nowadays also we have large language models that can code pretty efficiently. But still, you really need to make sure you understand what you are asking the LLM, and you know what to ask, and especially you need to know the answer, how to interpret the answer, because if you tell the code these two images do not overlap, do something about it, it will take one of the many possible functions that do this, and you need to know if it's what you need to do. I have had many thesis students turn on projects, and in the last year, they give me like 300 lines of code per day, and debugging them is, which run, of course, because if you use an LLM, the code will run, it will compile, but finding out if it really does what it wants you to do takes really a lot of time. So I don't know if, so the scope of this part of the lab is to learn how to see how the theory works in practice, and to show the challenges that you're encountering in a standard setup, in some very standardized analysis with like 6 or 7 lab experiences. It's not like that we are gonna have very complex algorithms. But you will need to see the challenges that you encounter and the typical errors that you have. So I don't know if you have any idea about, if you want to change the methodology, I can use the same blind notebooks, and you can even maybe use coding agents and see if the output is correct, and we focus the time on interpreting the output. I don't know if we want to do all the theory in the first weeks and then save the lab experiences for later, or to do that differently, or if you have any idea or best practice for that you've seen in other courses, or what. Okay. Okay. Okay, so I will keep mostly the same structure, and maybe this year it will be, you will solve the experiments differently, but it will be really interesting to see, to take a look at what you get, at what you write in the notebook, and how to interpret them. So it's, let's see. So I've put here a link about a very recent article by the Harvard Business Review about the use of AI programming and AI code. It turns out that in most offices, the use of AI wasn't reducing workload, it was increasing that, but it was shifting it. And here is a very small extract, because it turns out that many people who weren't coders started coding, and it turns out that this generated a lot of the so-called technical debt. So you have 10 times more lines of code. It takes quite a bit of time to maintain that, to debug them. And engineers kept on needing to work to fix bugs and completely work with partially finished pull requests. So, I mean, AI for coding, at least in my opinion, now works extremely well, but it introduces some problems in maintaining that and in checking that. And the more code you have, the more difficult it is to make it sure that it does exactly what you want. Okay, so that was just an introduction, just to finish the overview of the course. The examination, concerning the examination, this course is, as we said, it's just 3 credits. It's pretty fast, so, and we have only 7 hours of theory. So we will have a final examination composed by some theoretical question, especially because it's mandatory in these in all degrees. I think in BCOC, I'm not sure whether it's in BCOC or in Italy in general, to have an individual part of the exam. And we have mostly a short laboratory project. This one will be a group task, and you will need to present your work. I will provide you some data and some possible ideas for the analysis, but you will also be able to choose your own if you want. There are many websites with challenges online. And also for to assess the theoretical knowledge, you will be asked individually questions about some scientific papers that use AI or machine learning in a clinical task. Okay, so that's it. No, I will provide a collection, but again, if you are working on this kind of topic, if you have a personal interest and you want to get another one, you are free to choose your own one. We will repeat them. I will repeat them in the last lecture, but in any case, just for the sake of just to be sure, I will ask you to send me the paper before that you choose beforehand. Okay, other questions about the course, this overview, or anything else before we start? Yes? Uh, that's a non-issue, and we will, I mean, I will, we don't have, non ce n'è manco una qua. Perché io di solito porto giù una multipla, non siamo in tantissimi. Ok. Okay. We will, ok. Ok, qua ce ne sono un po'. Questi sono sventrati. Io vi porto giù una multipla. Oddio, questo non mi fiderei che è svitata. E sì, vediamo di arrangiarci così. Poi the code that I will that I used in the last years were mostly things that you can run on your own laptop. You don't need special resources. It's things that I also run on my 3 years old computer. Other questions before going into the first topic? Okay, so prego. Before. Okay. The issue. Okay. problema è che spesso me le miglioro un po' all'ultimo, però sì, lo vedrò di farlo. Okay, so the first topic is that of digital images and medical images, a quick summary about things. Some of them might be trivial for some of you. It depends on which previous courses you have followed. By the way, that's separate from the topic of today. But if I ask you to write a UNet, a trivial UNet for denoising, like the simplest one, will you be able to do that? You have seen it in other courses? Yes. Yes. So you did you never tried coding it? Okay. Yes, Keras or PyTorch. Okay. Did all of you do that in other courses? Okay. Okay, so you? Yes. Okay. Okay. And some convolutional neural networks in... Okay. Well, so you tried writing one. Maybe not a UNet or the other, but a CNN. Okay, that's enough. Let's say just to be sure. By the way, if it's okay for you, I will just go straight till the end and not do any break and finish earlier. Is that okay? Perfect. Okay, let's start here. So this might be trivial, but what's a digital image? A digital image is just a matrix. So what's on your computer? It's an array or tensor of numbers. Like you see this test image, you zoom in, you start to see some small squares, and you take a look at it, and it turns out that it's a number here, and to every dot, which is called a pixel, which is short for picture element, there is a value. We have said this is a matrix, and what's the dimension of this matrix? It can depend. It can be 2D, because you see on the screens are 2D, so in general you have for every position one number. But also in medical images, very often you can have 3D arrays. You have 3 positions, X, Y, and Z. You have a volume. But also in 2D, you can have multi-channel values. This is the standard picture that you take with your camera, with your phone, with your smartphone camera. You have X, Y position, and C is the color. So you have 3 channels, in this case, red, green, and blue. And you have an intensity value for every channel. We talk about 3 when we are talking about visible images with cameras, but it really might not be 3 if you are analyzing a microscope image when you have a fluorescence at different wavelengths. It might be 7 channels because you have a fluorescence at 7 different wavelengths. And then you can have lots of other possible dimensions, and they all make sense. You can have a 2D time series. So it's again a 3D matrix where you have XY over time. That's like a movie. Or if you have a color movie on your computer, that's 4D, XY, time, and color. And you can have all possible combination, even up to 7 dimension. It will be really an issue how to show on screen something which is 7 dimension, but it's not really something that absurd. There are some MRI images of the heart that shows you the speed and direction of the speed of the blood flow in the heart over time, because as the heart beats, you have blood going in and then staying still and then going out. And that's, you have a vector of speed. For every position, you have a 3D vector, which is the speed of the blood over time. Now, I have said that for every position you have a value. And they really didn't mention what the value was. We have, and actually this is quite important. The most common one that you have when you're working with natural images on computers is a bounded scale, where you take a picture with your camera and you get a number which is from a minimum to the maximum. And so in general, it will be either from 0 to 255 or from 0 to 1, as you wish. But in medical images, and not only medical images, you can also have an arbitrary unbounded scale. You mean this is a meaningless number. So you have, in one pixel, you have 2,600. What does it mean? We don't have any clue, but it's higher than 1,000. And so you have some relative contrast between what is high and what is low. This is typical for many MR images. And you can also have some other modalities where you have a physical scale. So when you do a CT scan, you will see that what we measure is the density, in every pixel, the density of the material that is present there. And so it makes sense that you associate it with a unit of measure. So you say this pixel has a density of 100. Or if you have a modality that measures the concentration of some drug, you will see you have 2 milligrams per kilogram of body of that molecule in that pixel. And how do we save it? That's the numerical format. The most common one is unsigned integer of 8 bits. This is the most common one we use with photography, with pictures. And given that this numerical format goes from 0 to 255, that's why I told you that when you have a bounded scale, in general, the numbers will be from 0 to 255. This is the most commonly used format in medical imaging, because if you think about it, you can convert it to any scale. If you multiply by a slope factor and then you add eventually a translation, you can divide the whole range of intensities with a very fine spacing, because you have 65,000 intervals, and you can convert it with a single scalar to any unit of measure that you might need. But here it's using only 2 bits per pixels. This one is if you work with floats instead, that's the best format for processing, because it does not truncate anything. But of course, it requires twice the space in memory or on disk than this format. You always need to be careful when processing data. When you load the image, you need to take a look at which format the reading routine is returning, because if you are using integers, 8-bit integers unsigned, you very quickly run into problems, like if you do the subtraction of these two matrices. You even get different results in MATLAB and in Python, because if you do 0 minus 2, you get 0 in MATLAB because it truncates negative numbers, or 254 in Python because it goes back from the top. And again, the division is even worse, because if you divide this number by this number, you get 3. And you lose all precision. And by the way, these are the results in MATLAB, because if you do it in Python, it automatically converts does the division in float. By the way, keep in mind that when you're working with integers, and most of the time when you work with images, when you lose some data, there are no ways to recover that afterwards. So even if you're using 16-bit integers, if if you do like this operation of dividing by 300 and multiply by 300, you lose all of the precision, which can be pretty relevant. And if you're working, like if you take your phone and you start correcting the contrast and the brightness of an image, and you save it and reload it after having saturated the whites or the blacks, you cannot recover any details that you clipped because it went too low or too high. That's something that you need to keep in mind, and that's why when we process, it's always best to use float images. Now, we will talk later about the space on disk that images occupy, but nowadays maybe it's not that much of a problem, but up until 10 years ago, an MRI scan was really massive. Like an MRI of a subject would have been like 20 gigabytes. So when you are in hospital and you need to save, I don't know, like 300 MRIs a day, and you need to store them for, I think it's 10 years, the limit given by compliance for legal reasons, you see that it adds up extremely quickly. Nowadays it's much cheaper, but again, now, given that it's cheaper, the result is that people acquire more images per patient, so it doesn't improve that fast as you would expect. Any question? So let's go to quickly introduce the topic of image perception and display. We will come back later in the later part of the course when it turns out that when we will see how radiologists actually read images to make a comparison with what a computer might look for in an image. So but this is a topic that covers psychologists, cognitive psychologists cover, and to study how the perception works. And it takes a whole, you could spend 8 years of 2 degrees studying only that, and we will skip over that over 15 minutes, but some basic concepts are quite important here. Now, I will maybe say the human eye, but actually it's not really the eye, it's the whole complex of the crystalline, which is a lens, the cornea, which is another lens, then the retina, which is a sensor, and then the brain, which does all the processing. So what we should be talking about is the visual system, which is the combined effect of if the signal arrives focused, if the retina is able to pick it up, and then how your brain processes it. It turns out that your eye can see things over 7 orders of magnitude of levels of brightness. You might need a bit of adaptation, but that's really a lot. We will see some examples now. But your eye is sensitive mostly to brightness over a small range, whether it's linear, of about a factor 100. These are all situations where you can see. Now, probably you cannot see much in a night with clouds and without any moon, unless you are in a city and you have all the reverberation of artificial light. But if you have a night with some clouds and the moon, I don't know if you ever experienced that, but even if you are in the open, in an open field up in the mountains, far from any artificial lights, you can see enough to walk without stumbling. You can see the ground well enough. At the other extreme, if you walk in a glacier in the summer, you have probably even 100,000, and that will maybe start to damage your eyes, but you can see. So we are talking about 7 orders of magnitude where you can walk on. Clearly, if you go from one situation to the other, you don't see anything, but if you wait 10 minutes, you are able to see in all these kind of extremely different situations. By the way, here you see mostly in black and white, and here you see mostly in color, but it's really amazing how well you can see. This is, by the way, your light response is not linear. So if I start from here and put intensity 0 and here intensity maximum, yeah, you will perceive something like that. Well, actually, you're perceiving it because this is really computer generated. If you take the a power function of that, actually you perceive this slope as perceptually linear. So you have more sensitivity over the brighter part of the spectrum than to the darker one. So just to summarize that, we have we can achieve this sensitivity by plotting the intensity on a logarithmic scale, and the fact that our eye is able to adapt. And now let's talk about what are the parameters that are important to recognize something. If I take this image, it's hard to spot most things. You don't see much, but if you take this image, you can notice that human vision relies mostly on the difference between colors or between brightness. You don't really care that something is dark or bright. You really care about the difference between different areas, because if everything is white, that's the maximum information that you have. But actually, if you don't see any difference, you can't spot anything. And by the way, your brain is really wired in spotting contrast. Like if you take a look at this, we can maybe call it optical illusion. You could perceive that this is dark and this is bright, while this is the same color. And again, we can see it with this optical illusion here, where this color is the same as this color here. But you perceive it differently because your brain is really hardwired into correcting for shades. And indeed, there is this concept of brightness constancy, where a surface looks the same under very widely varying lighting conditions. So this, if you went with the color picker in paint or something, you can see that this is almost white, this is pure black, but your brain tells you this is uniformly gray. And here is bright yellow, here it's dark gray, but your brain again thinks that this is uniform green, because your brain really interprets what it's seeing. Another thing is, another important topic is that of edges. Edges are actually the most powerful feature that we recognize. Just getting this sketch lets you understand a lot of the context. Here we have this kind of castle, and well, the quality here of the projection is very poor, but this is the original image. This is actually the gradient of the image, the spatial gradient computed by some routine, and you can see that your brain can really imagine, can really reconstruct this from just seeing this. You can already recognize what this was. And indeed, if I give you this image and this other image here, which have very different, a very small amount of blurring, to your brain, there's a massive difference between these two, which actually mathematically are very close to each other. But edges for ours are one of the most defining features that we have. The last defining feature is that of pattern. If I tell you what this is, you have obviously no clue. While if I ask you what this is, which by the way is a very simple sketch, it's not even a picture, you recognize a piece of wood. Because the presence of patterns, which are some regularities in the image, are really important to our brain more than to our eye, by the way, to recognize what we're looking at. And indeed, in radiology, this is what radiologists are trained to do. To summarize that, the prior knowledge enters massively in the field of vision. And you can see that from illumination. If you get this very simple sketch, you don't know what you're looking at. But if you just add some shading, that's the same image with a bit of a shade, your brain reconstructs a 3D ball in space, and it's just the exact same image with more light here and the shade here. I'm not sure if it's well, one of the most common definition of patterns is that of regularities. And in this case, I will not think that this is a regularity, but kind of. But anyway, this is just an overview because in the images that we will see, so which are proper radiology images, you don't get any of these artifacts. Well, maybe in microscopy you can have some non-constancy of the background. You can have that. Okay, so the next topic, probably you have seen this cited multiple times in different courses, in signal processing courses, and it's that of spatial resolution. And you might have wondered when you are looking at the specs of your phone camera, how many pixels do you have in an image? And you might ask yourself, how many do I need? You have the Fourier sampling theorem, also called the Shannon-Nyquist theorem, or the sampling theorem, or any variation. And it says that you can perfectly reconstruct any detail of a dimension which are bigger than kind of 2 pixels. This means that actually small images can still contain lots of useful details, and using more pixels might not always include more details. And there is also the field of image compression, which we will introduce also here very quickly, which is another strategy to make huge files smaller by removing details that we do not need. And we will need to talk a bit about what do we mean by we don't need that. So let's take an example of what this resolution is. This is a picture taken with my smartphone, and we have which has a resolution of almost 5,000 times 3,000 pixels. And I'm showing that it's a vertical picture. I'm showing that in almost as much space as I have. And do I really need all of these pixels? Actually, no, because if I zoom in, you can see it still perceive lots of details. And if I still zoom in, okay, here you can see some digital artifacts, but you can actually spot the individual grass filaments, and if you are taking the whole image, you don't see that. You could easily just take a quarter of the pixels. So just to sum it up, if you have 4,000 pixels and your screen has 2,000 pixels, you can zoom in quite a lot. And if we take another part of this same picture, you can see what happens if I add a lot of compression. Let's hope that you see that on this quality of this projector. Compression is based on some perceptual studies about what the brain is able to perceive and what it's not able to. And so what it does, you can reduce the size of an image by reducing the number of pixels. That's pretty effective, but you will the results will be blurring of the image. If you do compression instead, you will keep the resolution, because a well-written algorithm will keep the resolution, but you will discard a lot of details. So what happens? Like the sky here, which has lots of a very continuous kind of shading. Instead, here is made of piecewise constant colors. And also you get some weird artifacts, some like this gray here instead of brown, and you lose many other details. Now let's see if you can guess what are the standard dimension of images that we often look at. So a standard resolution of a movie, do you know what's in general the standard resolution? Ever wondered what? So a standard resolution of a movie, that's actually the proper name, the standard resolution. It's 700 pixels, 720 pixels on the horizontal axis and 576. An HD movie, you probably might have noticed that even on YouTube, if you click the quality, it's, yes. Yes, that's the standard, that's the more standard resolution nowadays. It's HD, which is 1920 times 1080. So a decent smartphone nowadays has a resolution of 5000 times 3000 pixels. And if you take a top of the line reflex camera, you might get to some 13,000 times 10,000 pixels. And we have made all the considerations about what we see. You will see that in radiology, we will work, except in one case, with very small pictures by the standard that you think that on your screen are like as small as stamps. So let's think about the file size. If you have a typical image, like a cheap phone camera with 4000 times 2000 pixels, that's 8 million pixels, and you have 3 color channels at 8-bit intensity. Nowadays, some professional film cameras or picture cameras have 10 bits of intensity depth. But anyway, this cheap image has 24 million elements, which results in 24 megabytes using integer 8. And you can see how it might explode very fast if you add like a third dimension over Z or over time without any compression or anything. Okay, questions so far? Now, we have our camera, we have our files on disks, and we need to look at the images. So what we have is the screen, which is very important, by the way, because if you are a radiologist, since the last, I will say, 15 years, you only do readings, which is the technical term for the act in which a radiologist gets the legal document about the diagnosis. The radiologist does that using a screen. So it's actually it needs to be certified. And a screen can only show 255 intensity of lights for each color. Some professional radiology monitors can have 10 bits of resolution. Therefore, the ambient illumination of the room where the reading is being done is fundamental. Together with the screen calibration, you actually need to certify the response of the screen, and it needs to be certified every couple of months. And because we have talked about the eye nonlinearity and the influence of ambient light, for sure you have the experience of when you have too much light coming in that you need to close down the curtains and so on. And also we have seen how the eye needs adaptation. Like this is the exact same picture, but with reduced contrast, and here you probably don't see any band. Here you see them limited, and just here you see them fully. So actually the part of the screen is relatively important for the radiologist. And there's another issue. I might have told you before that on many imaging modalities, you have 16 bits of depth to save the colors, but the screen can only display 8 bits, maybe 10 if you have the most expensive one. But anyway, you might, even if you have 10 bits of color depth, you will perceive 8 unless, or maybe 9 really if the room is perfect, because you see, I've told you that the eye sees linearly around 2 orders of magnitude. So what happens if you want to see 4 orders of magnitude? You have to apply what's called in radiology windowing, and also you could also apply lookup tables. So suppose that you have this test image here, which has lots of features. This is a test image. You have some very low contrast small dots, some high contrast dots, some very intense value over there. And what you can do is you decide to show only the intensities between 2 limits. And this image here, it's a test image that you can find in Python, and it's bounded between 0 and 1, and you say, okay, let's just take a look between 0 and 0.2, and you get this image here, and you're able to spot this low contrast, low intensity feature here, but you lose all of the contrast between all the other regions. Instead, you can also look only between 0.1 and 0.3, and you don't appreciate this, the difference in color between here and here, but you can see very well all of these, the differences here. So you are restricting the use of the whole color range to some sub-range. This is extremely common in radiology, and there are also some standardized way to do it. You can also apply, on top of windowing, you can also apply some lookup table. Windowing is defined like that. You have, if you want to see that mathematically, you have a function that takes 3 numbers in input, a value, a lower threshold, an upper threshold, and gives you the output in a range between 0 and 1. How it's done? Clipping everything that's lower than the lower threshold, clipping everything higher than the highest threshold, and linearly scaling everything in between. Pretty trivial. The lookup table, I'm sure you used it a lot of times without ever noticing. For every value between 0 and 1 that you get in output from the windowing function, you assign 3 values in output, 1 for each of the color channels of the display. So in the past, in Italian, there was this term which was falsi colori, fake colors, which renders perfectly what you're doing. You have a black and white image in input, and you output something that has colors, but the colors are completely made up. So this was one of the most common lookup tables, or otherwise called color maps, and it associates low values with blue and the highest values with dark red. And this means expanding your space just from the grayscale space, where your eye can perceive only some differences, to many more, to use a much larger space, because your brain distinguishes color quite a lot, so if you can perceive more details. What's the deal with that is that I've told you we are completely making this up, some random colors, and associating them with intensity values. So there is no single way to do that. And just in, if you look in PyPlot, these are a very small subset of the color maps that are present, and you have lots of them. These are some examples of some that you can use. I don't know how much you've used IMShow in PyPlot. And you have 3 parameters that do this. There's vmin, vmax, and cmap, which is do these 3 concepts that I've told you, 2 concepts, windowing and color map. And you can see how, depending on the color map that I've chosen, using the same windowing, I can highlight some details more or less. You need to be pretty careful when doing that, because there are multiple issues. And one first that you always need to remember is that like 20% of males and, if I remember correctly, and 5% of females are colorblind. So it's not really, well, even if it was a minority, that would be important, but it's not even a minority. And then also, you need to keep in mind that they might introduce some visual artifacts. There's the case of the so-called jet color scale, which nowadays isn't a default anymore. But you can see that there was this paper in 2007 that said that the rainbow color map is still considered harmful. That was in 2007. In 2015, there was a paper saying, why do we use bad color maps? And this person was saying, our goal is to supplant rainbow color map, because it was still used 10 years later than someone saying it's still bad and we know it. And well, in 2021, there was people still saying, don't use that. It's, they used to, nowadays in Python, it's the default is called viridis, which is called perceptively linear, because otherwise, if you took this linear ramp, this color is linearly moving from black to white or white to black. When you have a change of color, your brain automatically believes there is an edge. Says, if I'm going to purple, from purple to blue, that there might be an edge. While if you're going from one shade of blue to another shade of blue, the brain will say it's mostly constant. So here you are seeing, like here, 1, 2, 3, 4, 5, 6 bands, while there is actually no bands. So these, you might end up introducing apparent artifact on the people who's looking at the image. And last very quick topic, we'll deal quickly with that, is that in medical imaging, we often deal with volumes more than with planar images. How do we look at it? We just cut the matrix in 3 ways along the 3 dimension, and we get to see the same object from 3 different points. Like if you have a NumPy array, you can just slice over dimension 0, dimension 1, and dimension 3, and you display the 3 images. That's not really a complex context. We will not write a visualizer, but sometimes it might be useful to visualize what you get. Okay, let's do maybe as a last topic, let's see, let's see the cons. Yes? Okay. 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 No, there are no types of generally used of this kind of windowing. And sometimes there might be what's called a gamma function. So what's within the window might not be linearly scaled, but maybe scaled with a power law. But that's it. Then within the window, you just display everything that's present. Other questions? Okay, let's talk about image noise. So if you think about how you define noise, if I asked, well, I come from the physics department, if I ask physics students, and probably the same will be with you who studied statistics, how you could define noise, and I show you this image, we'll say, we'll put measure what's the standard deviation here, and make a difference and do this kind of calculation. Mean value in the signal, mean value in the background, and let's take the ratio between signal and background divided by the standard deviation. And well, it will turn out that this is what we do in the end, but this has lots of limits and we will need to be aware of them. Because what's the limit? This image has exactly the same signal to noise ratio, but if I ask you whether this noise is the same, I think that we can all agree that it's not the same. And also, is the background variability a useful concept? If I ask you if you can see the signal equally well, in these two cases, you probably will say no. And why is that? Because intuitively, the scale, the spatial scale of this noise is different from the spatial scale of the signal. And indeed, there can be many kinds of noise. There is the low frequency noise. There is the Poisson noise, which looks different from the random noise that I've shown you before. And also there can be some high frequency noise. You can see here that we have some kind of streaks. The noise has some kind of correlation, but it's very different from this correlation here. And also, if I take a slightly noisy image and I run it through the JPEG compression a lot, I get this thing here, which might not really be noise because it's not random, a random statistical process, but it's still noise to us because it limits our ability to see things. So for many practical purposes, this is noise. So you have to remember that we have a kind of task-specific definition of noise. If we have here a signal which is 10 pixels wide, and I add some very high level of noise, here my signal is 1, my background is 0.1, I add a noise which is higher than the signal, I don't see anything. If I filter it with a spatial filter, I recover it extremely well. But if my signal had been smaller and I apply the same procedure, I remove the noise, but I cannot distinguish anymore this signal from this noise. Also, you need to remember the human perception. If I ask you which of the two denoising is optimal, probably for a computer, this one will be the best one, but for us, it will be this one because we preserve more edges, probably, but there is no statistic definition. I mean, there is not univocous definition of that. The noise can come from lots of different places. The most common one is the fact that we count individual photons. Whether you are taking a picture, especially in the night with your camera, or taking an X-ray, you limit the number of photons that you shoot because they're dangerous, and so this results in noise. It can, depending on the regime you're working in, it can behave as a Gaussian process or a Poisson process, but that's not super relevant in this course. You can also have some background counts from the electronics of your detectors. You can also have some noise introduced by all of your processes. Okay, let's skip these definitions. And so we have some metrics of noise. This is the one that I've shown you. You have one of the most common ones is the mean square error. You take, which indeed will be a very common loss function for all the AI-based processing that we do, because it comes from Gaussian processes, Gaussian assumptions about the noise. From that, we can get a peak signal to noise ratio, which is just using a logarithmic scales to compare the mean square error with some dynamic range. And this metrics works only when you have a gold standard. Just to show you, there are some limits to the mean square error. Suppose you take this image here, and it turns out that all of these 6 images have the same mean square error. And you might ask yourself why, because I guess that your brain likes this image maybe even better than the original one. This one might not even look too different from the original. This one is what you would call noise. This one, if I ask you to define that, you will probably say that's a normal image corrupted by some bad pixels. These one are compression artifacts, and this one is without noise but blurred. And some people introduce an alternative metric, which is the structural similarity index metrics, which instead weights more the factors that are important to your eye. So it weights the luminosity differences in the mean luminosity of the image, contrast differences, and the correlation, so the amount of edges. And if we take the 6 images as before, this is the original one. This image here, which had just a higher contrast, indeed has a similarity metric of 0.92. This image here, which had a different brightness, has 0.987, so like 0.99. This one, which has this corruption, goes down to 0.73. This one to 0.58, and the blurred one to 0.64. So you can see that this is much closer to our visual perception. So why do we care about about noise? If you have an imaging modality that uses ionizing radiation, the bad ones, to clarify it between ourselves, turns out that less statistical noise results in, if you can reduce noise, you can give less radiation to patients. Or you can reduce the time that it takes you to acquire an image. Also, if you have incomplete data, these introduce some pattern specific, some noise with a specific pattern, and if you are able to remove it, you can reconstruct images that are not fully sampled. And like if you have an MR image, which might take 20 minutes, half an hour to acquire, that will really benefit from a shortening of the acquisition time. Okay, questions about noise? Okay, so let's introduce let's pivot to medical imaging, and let's just introduce for today what kind of medical images exist. They can be classified in according to multiple criteria. One is by the department of the hospital that acquires them. And in this case, you have radiology, which acquires large-scale images with X-rays, magnetic resonance, ultrasound imaging, and emission tomography. You can also deal with visible photography. If you go to a dermatologist, they will take pictures of your skin lesions. If you have endoscopy, they will put a camera maybe in your stomach or in other cavities and look with a camera at without any specific magnification. Then you have microscopy that still deals with visible light or maybe with fluorescent staining, but you have lots of enlargement. And in a way, also these ones, they are not really, well, these used to be really images because you were acquiring an electrical signal and printing it out. Like if you do an electrocardiogram, I don't know if any of you ever took one, you really get, they were printing out a line, the plot, on a piece of paper, and that was the source of the reading for the physician. You can also categorize images according to the purpose according to which they were acquired. So many are show the anatomy, which means the shape of the body or of organs. And you can use X-rays, which show the density, and so different organs so generally have different densities, so you see boundaries and therefore shapes. Magnetic resonance is sensitive to chemical composition, so like even within an organ you can see blood vessels, fat, water, you see them extremely different, and the relative shape of each of these parts give you a pattern of healthy / non-healthy. Ultrasound sees structure boundaries. Otherwise, you can also look at properties, like with nuclear medicine, you can see the accumulation of a drug in different organs, so, or even within an organ, so you can see if there are parts that work differently. Or you can see that in magnetic resonance or like dermatology, microscopy, and so on. You can also have you can also categorize using dimensionality. So a printed signal like an AKG is a 1D line. An X-ray is a 2D picture, like here, the typical X-ray of an arm. A tomography, you have a 3D stack of 2D planes. So it's not really, you could call it 2.5Ds because you have a much lower resolution along just one of the directions. You can have fully 3D, so which means you have equal resolution of along all directions, and you can also have surface renderings if you want, like 3D models for displaying. An example of what I mean by the tomography, this is actually a pretty normal way to acquire the NMR of the brain. The pixel size is 0.8 millimeter of this MRI times 0.8 millimeter, so you can see the gray matter and the cerebrospinal fluid with extremely high level of details. While if you go in the other two directions, you can see that it's extremely blurred because the slices are 5 millimeter thick. So if they are 5 millimeter thick, you can see them pretty blurred due to the sampling theorem that we mentioned. Keep in mind that I've mentioned before that we have pixels in X and Y dimension, and what you generally do in all of the modalities, for sure in radiology, for microscopy maybe it's different. To every pixel, you are able to assign a physical dimension. So you say, when you say I have these two features are 5 pixels apart, you can translate that into millimeters. This is not trivial. Like if you take a picture of this garden, let's say, and you cannot reconstruct the distance between how wide that window is, because you don't know the magnification, the distance. You can just which kind of objective you were using, if it was zooming or very wide or anything. Now, to summarize, we can summarize this way using the spatial resolution and the sensitivity to concentration of some chemical substances. When you're working with X-rays, you can go down in spatial resolution to less than 100 micrometers, but you don't distinguish different tissues very well by their chemical composition. With MRI, instead, you can have a much higher resolution. With human MRI, you're generally limited to 1 millimeter, half a millimeter. With preclinical, which means small animals, so mice, rats, you can go to less than 100 micrometers. While if you are working with nuclear medicine, you have very poor spatial resolution, like 1 centimeter, so very poor. For 1 centimeter resolution means that you image the abdomen of a human adult in 50 pixels, just to give you an idea. And when you're going with microscopy, you can go down to 1 micrometer. But of course, microscopy is, nowadays there are some types of microscopy for dermatology that you can acquire to see even in depth in vivo, so which means live on yourself. But in general, you take a biopsy, you do an operation, you open up, you extract something, and then you go to the lab 1 week later. So it's very different from the X-ray, which takes 1 minute to acquire and show. Last type of category is the use of ionizing radiation or not, because ionizing radiations are bad. And so we have modalities that do use ionizing radiation, which is X-ray and emission tomography, and modalities that don't use it, which is magnetic resonance, ultrasound, optical imaging, visible imaging, microscopy, and so on. So I can dedicate the last maybe 5-10 minutes to some elements of radiation safety, just for your own culture. It will not be relevant to the context of this course, but it's useful to know when something is dangerous or not. So let's talk very quickly about radiation safety. By the way, technically I'm certified as a medical physicist, so I'm allowed to work in hospitals to check the radiation safety of the patient while doing images. So how do radiation do damages? Actually, the way that it works is extremely simple. It's not really some obscure quantum mechanics mechanism. It's that in 70% of the case, they ionize the water, they create some free radicals, and this reacts with the DNAs and breaks the DNA chain. In 30% of the cases, the radiation directly breaks the DNA of your cell. This is like most chemical substances do. And free radicals are, maybe you've seen it in some cosmetic advertisement that they are bad. Indeed, they are. And if you break the DNA only once, it's mostly irreparable. If you broke it twice, it's mostly unfixable. This is an effect very similar to most poisons, and there is nothing special about radiation compared to other chemical substances. And the dose is measured in this unit, which is called sievert. The effect can be divided into stochastic and deterministic. Deterministic means they will happen for sure, and they will happen straight after the exposure to the radiation. It happens at around from half a sievert onwards. And they also, they are larger, the deterministic ones are larger the more dose you get, and there is a threshold effect. The typical effects are skin burn, hair loss, infertility, cataract to the eye, and in cases, malformation of the fetus. And if you go to very high levels of radiation, and not just to maybe to the skin, you might end up with acute radiation syndrome, which might end up in death. On the other side, you have stochastic effect, which means you get a probability of developing mostly cancer over the rest of your life, and like any other poison. And this is for very low levels of exposure, but continuous. And the effects depends also on the sensitivity to radiation of the cells, which, by the way, is much higher in the young population. The younger you are, the more years left you have to live, and both your cells are more sensible. And there is no known threshold for safety. Now, the average radiation dose to an American person is 6.2 millisievert a year. And medical radiation, by the way, for the average subject contributes to half of that. And for that, there is a huge variability between the population. And there is like half of that becomes from the natural background presence in the rock and in the concrete. And you can do anything about that. And it varies really a lot depending on where you live, because if you are like in central Italy, in regions where homes are full of turf, this emits a lot of radon, so you get a lot of radiation. If you are near thermal bath, also they are full of radon in general, and they give you radiation. If you are somewhere else with other kinds of rock, you don't get it. You get lots other kinds of radiation from potassium, which is a natural element needed for your body. You get many from cosmic rays, which are much more if you travel with planes, of course, because there is less shielding. And then you get all of the radiation from medical imaging and occupational and industrial exposure, or from, let's say, radiation pollution is pretty rare. So I said the average is 6.2. How many do we get with a medical exposure? It depends, really a lot. If you do the X-ray of the hand, you get 0.005 millisieverts, so nothing for any practical purposes. The typical bite wing exposure done by the dentist is 0.04. A chest X-ray is 0.01 as compared to the 6 of your natural exposure, a mammogram 0.4. When you start working with CTs, you start getting to something which is higher than the typical radiation dose. And if you do a chest CT, a chest plus thorax CT with contrast media, you can get to 20. So it's kind of a non-trivial dose. So the takeaway message here is that most procedures have negligible radiation dose, but some specific procedures, especially if repeated and in young age, can actually be harmful. Now, a chest CT is not really common, so if they ask you to do one, probably you have a pathology which really requires it, but these should be minimized. So that's why you can just say, if you have like an injury and you are asking yourself, should I have a chest X-ray or a CT? Even if the X-ray is much less precise, it might be worth doing just that. And okay, I say that, well, let me just talk about the two file formats that we will work with. There is the DICOM file format, is the digital imaging and communication in medicine. It was invented in the 80s as a standard for all medical images, from pictures in dermatology to CTs. Therefore, it includes a possibility for a huge set of headers that you can modify. It can encapsulate different kinds of images within itself. It also handles the network communication within the hospital to allow images to be seen from all the departments. However, due to this huge interoperability, it is very bulky, it has a gigantic overhead, many headers fields are non-standard, and so it's a bit of a pain to use it. The Nifty file format, which is the other one that we will use, is used in neuroscience for research only, because DICOM is used for the clinical side, so it needs to be compliant to lots and lots of standards of reliability, while Nifty is used by the researcher, so it's only has a 348 byte of header, so you save like 3 or 4 parameters and that's it, with just orientation information, and is used only in neuroscience, but massively. And some other resources, there is this website which is called the Radiopedia, which is designed for physicians and is pretty popular with them. So it has a multiple description of pathologies, it helps you with the anatomy, has very short summaries of useful information of most radiology techniques. It's a for-profit website, so it's annoying and it's getting worse with time, but it can still contain a lot of useful information. Okay, so that's it for the first lecture. Any question?